Thank you, Dr. Abdullahi, and thanks to Professor Tagharat. I will continue the webinar. The title of this part.
I suggest someone you first share your screen yourself, that you have better control on your computer, please. I will stop sharing. If there is any problem, I will continue working that.
Okay, I forget. No. Everything is okay?
Yes, everything is fine. Thank you.
Thank you. The title of this part is Oil Spill Monitoring and Cleanup. And as you know, marine pollution caused by oil spills is a severe environmental issue that may cause adverse effects on marine ecosystem. Offshore oil and gas exploration, the production, and tanker vessels are the major source for oil spills. Statistics indicate that in spite of a downward trend in the total number of oil spills, they are continuously reported in different regions. For example, recently in January 2018, an Iranian oil tanker, Sanchi, carrying greater than 100,000 tons of light crude plus its own fuel, collided with a freighter and exploded. In reaction to such accidents, some projects are started to develop modern tools to support emergency response. And you know that the Persian Gulf as a hub for oil industry is under permanent threat from oil spills due to the oil exploration, production, and transportation. In recent years, several spill events have been reported in the Persian Gulf, and oil spills have continued to occur. So it's necessary to plan for emergency response in oil spill in order to protect the unique ecological resources in this Gulf. As you can see, oil fields are hot spots with high probability of oil spill. The risk map of the spill source is shown in this slide. As can be seen, the frequency of accidents in the oil field is expected to be higher, and it's high. Using this risk map, it's make it possible to identify high risk sources, and then risk management program should focus first in these areas. About the application of swarm robotics in oil spill, I should mention that although autonomous robots application for this purpose are currently in an embryonic stage, but different agencies like British Petroleum or Shell incorporating them into oil spill cleanup and monitoring. Several researchers have proposed solutions based on unmanned vehicles or swarm intelligence for developing oil spill response that are safer and more precise than the use of manned aircraft or manned ship. And drones have the potential to deliver information quickly and economically for the areas of difficult access. And you can see some example of the use of USVs and UAVs for this purpose in this slide. For example, DESMIM is developing a drone for burning the oil on the surface of the seas. Or UAVs are mostly used in monitoring purpose. And you can see this video use booms for ocean cleanup.
Trillion pieces of plastic float at the surface of the Great Pacific Garbage Patch. Here, the ocean cleanup is the world's first technological solution to this growing problem.
Please increase the volume of the sound because we don't receive the sound properly.
The system consists of a 600-meter-long floater and a 3-meter deep attached below. The floater provides buoyancy to the system and prevents plastic from flowing over it, while the skirt prevents smaller particles from escaping underneath. As the impenetrable skirt creates a downward flow, marine life can safely pass beneath it. Here is how the system catches plastic. The system takes advantage of 3 natural oceanic forces: winds and currents. Both the plastic and system are being carried by the current. However, wind and waves propel the system only, as the floater partly sticks above the surface, while plastic is not just beneath it. The system thus moves faster than plastic, allowing the plastic to be captured. The skirt extends deeper in the middle of the system than on the outer edges. As the current applies pressure on the skirt, the system naturally adopts a U-shape, which enables it to concentrate plastic in its center, like a funnel. The drag generated by the skirt also acts as a stabilizing force, allowing the system to reorient itself when the wind changes direction. And because the system, like the plastic, is free-floating, it automatically drifts to the areas with the highest plastic concentration. Fitted with solar-powered lights, collision systems, cameras, sensors, and satellite antennas, the system actively communicates its position at all times and continuously gathers performance data. Periodically, a support vessel comes by to take out the concentrated plastic, like a garbage truck of the ocean. The plastic is then transported to land, recycled, and made into durable products. This is the first of a fleet of 60 systems. Once deployed, the fleet is expected to clean up 50% of the Great Pacific Garbage Patch every 5 years.
Okay, I will continue. And now I speak about cleanup methods. We know that effective oil spill cleanup methods are mandatory, even if only seldom used. And 4 major categories of oil spill cleanup are chemical methods like using dispersants, physical methods by burning the oil, biological methods and using bioremediation, mechanical methods, and which is using boom and skimmers. Booms work like the video we have seen. For example, dispersants break oil into small droplets that mix the oil into the water. Or in situ burning is used in remote areas where the spill oil is fresh and thick enough for an effective burn. You should note that effective use of this method is limited in time and governed by the oil properties. So monitoring is important. For having a precise information about the location and real-time behavior of oil spill is essential to perform an efficient, which is help us to perform an efficient treatment of this environment catastrophe. Traditionally used helicopters, airplanes, and ships, and now potentially augmented by modern UAVs. During a flight, the UAV collect data, equipping responders with everything they need to make the right decisions. UAVs are the eyes in the sky. Having an eye in the sky quickly is one way of managing response and reducing the impact on the marine environment. There are also other significant benefits for human health and safety to not deploying manned aircraft in such situations. And swarm robotics offer an ideal solution to perform such challenging tasks. And these benefits motivate us to utilize these advanced robotic techniques to monitor and track the propagation of oil spills to provide the necessary information for decision makers and for oil spill cleanup technologies. The application of this concept also may be extend beyond the oil spill problem and could potentially find application in risks in search and rescue, mission, or forest fire mapping, and application like that. One of the parts of our research is oil spill modeling. As I mentioned earlier, planning and decision making in oil spill response require an understanding of oil spill weathering process, its distribution on the sea surface over the time. And offshore oil spill modeling is complex, as the fate and transport of the spilled oil depends on several uncertain factors. Oil spill simulation models can be used to assist us for cleanup effort. For example, Genome. Genome software is a comprehensive spill modeling package to predict the trajectory and spreading of the oil pollution. Genome is capable to update and modify the forecast using new observation or new evidence from overflight data of UAVs, for example. Also, considering the stochastic nature of ocean and meteorological conditions and weather, the Genome can incorporate this uncertainty into the oil spill modeling. It's a good opportunity for us. In this slide, you can see the Genome software, and at first you should enter information that describe the oil spill scenario. What scenario? A scenario defines where, when, and how much, and what type of oil has spilled. You can see the model setting box here to enter the start date and the start time of the spillage, and then you should consider the wind data. Your wind could be constant, variable, and speed and its direction can be set, and then oil spill specification should be set. You can add a point or line source or a spray, and then you have the simulation oil spill. Main Genome output is a series of Lagrangian elements that you can see in this picture that are released from a spill source and transported by wind, current, and turbulent diffusions. The direct output of this software is information on the location of these Lagrangian elements in the latitude and longitude format, and their properties like mass, density, viscosity at each time step. And this output can be presented by animation, pictures, or Excel file or text file, which one you need. In this slide, you can see animation of oil spill. This oil spill is near to Abu Zar oil field, which has a high risk. And in this scenario, 300 barrel of oil is considered, and you can see that the released oil spreads and moves southward due to the wind and current. The integration of this simulation data has significantly enhanced the effectiveness of oil spill responses. And for quantitative modeling, it's necessary to convert this data to quantitative results such as density function. Therefore, we used this data to achieve density function with the use of Gaussian mixture model. Usually the critical feature of the environment is modeled by a density function. And in our problem, we assume that the oil distribution on the sea surface can be described as a mixture of Gaussian kernels. So the spatiotemporal density of the environment is modeled by a Gaussian mixture model. Thus, the output of a genome Lagrangian model is processed to calculate the parameter of this mixture model in different time steps, which represent the concentration of oil on the sea surface. Be represented by speed, and the parameter K represents the number of oil slicks. Each component has two-dimensional mean and 2x2 covariance matrix that represent the position of the highest level of oil, the concentration by mean, and the shape and orientation of Gaussian kernels. In this study, the maximization algorithm is employed for fitting the Gaussian mixture model. And at first step, we clustered the data to determine the optimal number of slicks. And then the covariance matrix structure is selected. Both of them is selected by minimizing the Bayesian information criteria. Then the weight of kernels are calculated by converting this labeled data to concentration. Here you can see the results, and the proposed strategy is used, and in the picture you can see that the oil spills are decomposed in two slicks, and then after time the oil spills become unified and one oil spill we have. And then we focus on oil spill cleanup. We investigate the use of robotic networks for oil cleanup using dispersant methods. But and the main question is how to deploy the agents in the appropriate location to have an effective dispersant spraying. From practical point of view, the correct spraying strategy must be used to achieve the recommended treatment rate and to prevent overdosing or underdosing. This requires a proper understanding of dynamic behavior of oil spill and an accurate and effective spraying strategy. Based on this requirement, we suggest using a group of UAVs that each agent is equipped with a localization device, a dispersant, and downward spraying, as you can see in the figure. And the goal is to design a distributed deployment strategy for mobile agents that can autonomously track the oil spill spreading. Then in the optimal configuration, more agents gather in the area with higher contamination, and therefore the dispersant hit the oil spill at the desired dosage. And this strategy done in few steps. At the first step, we use the Gaussian mixture model we explained in the previous subsection, and this Gaussian mixture model describes the time varying behavior of oil spill as a density function. Then we developed a deployment strategy based on Voronoi partitioning, and this deployment based on the Gaussian mixture model that we have. Then the controller autonomously adapts the UAV configuration with respect to the oil spill distribution. And finally, spraying strategy is designed to reduce the overdosing and underdosing. because this dispersant methods are some of the time are toxic to the other parts of the ecosystem. And the control strategy we develop is distributed at the outer loop, a Voronoi-based trajectory generator you can see, and this Voronoi-based trajectory generator determine the new position for the UAV at each time steps, and to move to this new position, each UAV will use the integral terminals or super twisting sliding mode control in the inner loop. And based on this framework, the closed loop system converts to the centroidal Voronoi tessellation, and then the dispersant would be sprayed on the oil spill in an optimal manner. Dispersant spraying in our work is formulated first as a coverage control problem. And then this deployment problem is transformed to a target tracking based on the Voronoi partitioning, and by considering the nonlinear dynamic for aerial robots, a super twisting sliding mode controller is applied to track and the desired trajectory and achieve the optimal configuration. So this new controller ensures that the UAV's approach to the near optimal centroidal Voronoi configuration asymptotically. Here you can see the result. Deployment of UAV at different time instance is shown, and from top of view. Each UAV is indicated by a star, and the white line denotes the Voronoi itself. The colorful background reflects the spatial distribution of the oil spill over the mission area, and the yellow part represents the region with a higher oil concentration. You can see that UAV followed the oil spill distribution changes, and as the oil spill expanded, the UAVs followed this path of expansion. Okay, at the next part, we focus on the monitoring mission. In the context of robotic networks, estimation-based coverage control is an appropriate framework for this mission. We present a new approach toward deploying a group of UAVs as one of the most important emerging tools in monitoring missions. The goal is to design a framework to provide an estimation of the unknown oil density function with multiple sensor-equipped UAVs. We consider two different communication architecture for the robotic networks, including the centralized and distributed. In the centralized, the UAV just communicate with the server, while in a distributed one, UAV are just allowed to communicate with their neighbors. In the estimation-based control problem, agents estimate the parameters of an unknown density function, and simultaneously we need to coverage control that's implemented based on this estimate. In this work, Gaussian mixture model based density function is employed to model the unknown environment, and then expectation maximization algorithm is utilized to approximate the unknown Gaussian mixture parameters. And by this means, the learned oil density function is used to construct the control law, coverage control law. And we also, at the end, propose an adaptive sampling algorithm. This adaptive sampling algorithm can allow mobile robots to find more informative locations to improve the estimation performance. In this slide, you can see two algorithms, centralized and decentralized algorithms. You can see that in the centralized algorithm, we have two parts, the server part and the second part that denotes the operations executed by agents. And for adaptive sampling, in this work, we choose mutual information as a measure of information to force the agents to move toward unobserved region. In distributed algorithm, consensus-based expectation maximization algorithm is presented to learn the local density function, and each agent in the distributed algorithm work independently. And in the next slide, in this slide, you can see the results. And first, we consider scenario in the genome software and use the particle and elements as samples for the agent. And in the scenario, medium crude oil is released, and in the northern shoreline near to the northern shoreline of the Persian Gulf, and which has more risk, and we studied this part. And the monitoring mission started 1 hour later than the spillage starts. In this slide, you can see black stars that denotes UAVs, and black lines that denotes the Voronoi cells for each UAV. And the figure showed the snapshot, 4 snapshots of the 10 UAVs forming a network, and try to track the oil spill distribution. While you can see that only 4 of them can measure the oil spill particle at the initial state. We can see that the informed UAVs can drag all the other UAVs to move toward more polluted area in this mission region. The algorithm that's implemented in this slide is distributed. And in the last picture, you can see the evolution of coverage cost function. You can see that the proposed centralized and distributed algorithms work close together. And also you can see the effect of adaptive sampling algorithms. By using adaptive sampling algorithm and mutual information, we have the faster convergence rate as we expected. And the last part of this presentation is some future prospects. What I can say is we are in the first steps in this research, and there are a lot of steps still remaining, both in terms of theory and application. In this work, we basically focus on the development of appropriate and basic framework for swarm robotics in oil spill response. Of course, this algorithm should be implemented and tested on usual UAVs, and that we are trying to make it possible in KN2C. And of course, it should be flexible, and the failure of agents should be investigated. On the other hand, the performance of the heterogeneous system in our robotic network should be examined. We don't know what happened, or the efficiency of the network, how much improve using heterogeneous system. Thank you very much, and I wanna ask Professor Taghirat to continue the webinar, if any question.
Thank you, Samanov, for your very good presentation. I would like to have some time for questions, comments, and basically the part that other people would share through this webinar. You could, I guess, Mohammed, everyone can open the microphone by himself, or should raise hand and we should open the microphone.
Yeah, of course. I will let them to speak if they are. Raise your hands to ask the question.
Ali Pira has raised her hand. Please.
Okay, Ali, please. I ask you to unmute yourself.
Hello to everyone and to the dear professors. I'm the master student, and as a matter of fact, I myself am working on the swarm robotics, which is my thesis. I would like to know, you use the adaptive control approaches and why you don't use the machine learning approaches, which is so fast to converges.
Okay, very good question. Regarding choosing different approaches in terms of the control strategy, of course, we didn't talk that much about the control. In this webinar, we mostly talk on the consensus, on the formation, and on the particular swarm robotic aspect of the problem. But in terms of the controls, if you have the configuration and you would like to reach to that configuration, there are a lot of other approach available. Using artificial intelligence is, of course, a very, very good alternative, but I don't agree with you that it is much fast and without any pain. You know that there is no pain there is no gain. In terms of artificial intelligence and basically the deep learning approaches or learning approaches, you should spend a lot of time in terms of the learning process, and you should have a lot of basically data or save data for that. This can come after a long term of training processes. We prefer in this particular subject, of course, we have talked about this artificial intelligence in our previous webinars, depending on the subject. Of course, it is always a very good alternative approach, but in this approach, since we are using a model-based monitoring and approach, we prefer to have more classical approach for the control. Of course, you can use other approaches as well.
Thank you.
You're welcome. I would like to ask every student or participant who would like to make the question first, introduce yourself, that we can answer appropriately according to your needs. Mohammed?
Hello, can you hear me?
Yeah, of course.
Yes.
Please.
My name is Amir Mahdi Shahverdi. I'm a master student of aerospace engineering. I want to ask two questions. Question one, what is Voronoi? And question two, how do you solve agents communication? Does mobile network like 5G or 4G or something like that exist on the sea? Thank you.
Very good. Two basic questions. Voronoi approach, maybe someone can talk about it. Someone, can you give some explanation? It is better that I don't answer all the questions. Are you with me, someone?
Yes, I am here. Voronoi is a partitioning method, and in coverage control, especially in static coverage control, is a basic method. You can use a straight line as I used in these simulations, or you can partition your area for the agents by circles, and you assign each agent, and you can assume that each agent is a point. These points are the generator of your Voronoi partitions, and you can define the line between them with different methods. It's traditional method, classic method in Voronoi in coverage control.
Perfect, Samana. Just to complete this question with some rather more visualized answer, consider that if a soccer or football team is basically in a stadium, and the coach will specify a specific area in terms of defense or in terms of forwarding to each person. This is some sort of partitioning the 2D space that basically the soccer player are working. That is that's the essential idea of Voronoi partitioning system in a 2D environment. And your second question was on in terms of communication. There are a lot of ways to do the communication. Usually when the distances of the drones are not that much, Wi-Fi is a very good solution to have the communication as well. As I mentioned in our basic first slide, up to 500 meters, it is quite possible to have transmission of data, even the images, digital images through Wi-Fi facilities. Of course, there are other more sophisticated or more enhanced communication tools that can be available. It could be also satellite-based. It could be a different way on a central base, but usually all the drones that we have developed have the facility to communicate with the neighboring drone through Wi-Fi communication. Thank you. Any other question?
Dear Ali?
Yes. Can you hear me?
Yeah,
yes.
Of course, please.
Okay, this is Ali Safari. I am a postdoc at the McGill University. And thank you for this webinar. I have two questions. First, is the accuracy of GPS at the sea is enough for having formation control, actually to maintain the desired formation among the drones in the sea or not? The second question is that in your distributed algorithm, do we need any relative position estimation among the drones or not? If yes, what is the suggestion for that? Thank you.
Very, very good technical. I don't know, Ali, if I've seen you at McGill or not, but I wonder how you have been connected to our network to this webinar. You could maybe answer that later, but there are very good two questions. Basically, the first question was regarding the way, I just forgot how I would like to answer the question. Could you repeat again? Sorry. Ali? Can you open the unmute Ali as well?
Yes. Okay.
Yeah.
My first question was that. Okay, the first question is that if we want to maintain a formation among the drones,
okay. GPS.
Is the accuracy of GPS enough to maintain the position and avoid the collision among them or not?
Yes. Regarding the collision, it is enough, but GPS is not usually that much reliable, especially for such mission, such important mission as well. GPS gives you the global positioning, and this is very important. But as you know, that it could be somehow, it is not that secure in terms of communication security, and also in terms of precision, it is also not that much accurate. Usually, if you would like to use just GPS, you should have some sort of relative GPS measurement. This is not a new, but it is a more advanced version of GPS application that you can use in terms of some centimeters. You can get some accuracy if you just want to use single. But usually in a drone, we have sensor fusion. We have not just one sensor to be used or relied on to do that. And the way that we are working basically in KN2C is usually we use the image-based visual information and some sort of graph-based SLAM algorithm to find a very, very more accurate positioning of the robot itself. This is another area of basically research that could be easily, readily used in this type of application. But of course, regarding the second question that you have, this is also very important, that the relative distance is important. This is quite related to that relative GPS base that the people, the technologies involved. So usually one drone should have communication with the drones, the neighboring drones, which are not that far, so we can use different approaches to find the accurate way, and then we can have some sort of triangulation or get the other information to fuse into the just information of the own robot to work with. So relative distance is one way, or one very good way to find some such a solution, but usually a mixture of global and local positioning is used in such application. I'm sorry, I hope that this is, and if you can say how you have been connected to our network, that is quite interesting.
Okay, thank you for the answers. I just saw your advertisement of this webinar on LinkedIn, and just registered that.
In which department are you working, Ali?
Mechanical engineering.
And how is Jorge Angeles over there?
Actually, I don't know that person. I am
Dr. Angeles, Professor Angeles in mechanical engineering.
You know, I'm just right here.
You're new. Okay.
Actually, 1 year and a half, but mostly I was working with another professor, Professor Scharf. Maybe you know her.
Yeah, I know.
Yeah,
very good.
That's that one.
I wish you luck for your studies, and keep connected. Keep connected.
For sure.
Thank you. Thank you.
Another question from Professor Amin Hajizadeh from Aalborg University. Professor Hajizadeh, please.
Hello, Professor Taghirat, and thank you for this impressive presentation. In fact, when I saw your presentation, it was very interesting for me to attend this meeting. And now I know more about the robotics because my background is not robotic, but you know, in our department, in fact, we are doing some research in the area of robotic and subsea, robotic for oil and gas platform in Denmark. Always we are thinking about developing new energy storage for drone and robotic. And I wanted to ask you, how about in your research? Do you have any specific limitation during using energy storage? And what do you think about development new kind of energy storage for drone and robotics?
Thank you, Amin, for joining us, and happy to hear that you enjoyed this webinar.
Yes, thank you.
I usually say that if the presenter enjoyed the seminar, the audience will also enjoy. So it was very enjoyable for me to just give the presentation of other people's work to people. But a very good question as well. The drones, especially these small size drones, let me just give a bit broader answer because this is important. Micro aerial vehicle is a mechatronic design. When I say mechatronic design, it means that in the design of such a drone, it is very important to consider different aspects of the engineering in the design. It is not enough to have just aerospace or aerodynamic knowledge here, or just electronic or mechanics or let's say energy, as you mentioned. As you see, if you would like to have higher power, we should have more larger motors and basically propellers, and this give you larger weight, and the larger weight gives you lower maneuvers. So there is a very, very interesting optimal design in terms of the drones, how much it should be large or small depending on the payload that it is taking. And one of the basic and most important limitation of drones, of these small size drones, are limitation of energy. So usually the batteries that we are using usually ion batteries basically, and these are giving us, in terms of just to give you some intonation, gives you about 20 minutes to 30 minutes flight time, and this could be sufficient in terms of monitoring aspect, as you see in the movies that I show you. But for long-term work, this could be not sufficient. We need some larger drones, some larger drones, and some more energy to fly, and this optimization goes on. It is very important to have some sort of energy effective flying aspect here, and also some sort of energy recycling or regeneration of energy for the drones. And a very hot topic of research that I think in Aalborg, there are some researchers that I know that they are using in terms of the state-of-the-art innovative ways to get to recharge the batteries, or to gain energy from some natural sources. Like in Persian Gulf, we have a very good, in terms of heat and sun, we have a very good sunshine over there. But this is a very special topic of research, and it is not still not that much commercial. We usually use high-performance batteries and recharging recycled there. And since the drones are not that much expensive, we can have some for a special mission. Just if you would like to have one flying quadrotor, usually we use 2 or 3 to have. Thank you, Amin, for joining us.
Thank you, Professor.
Welcome.
Okay, we have some question in the chat panel from Irfan. Can I read it for you?
Yes, please, if you can.
Okay.
Just.
If we had a non-controversial weather condition, will system has their stability?
So in terms of the stability, and it is a bit more than stability. You should say resilience. It is not important, not enough to have stability, but it is enough to have resilience. To answer the question pictorial, I just refer to the flying aspect of the drones near the powertrains, as you saw in the movies. These experiments and this kind of flying aspect for the totally handmade basically drones illustrate that the concern of stability is well developed on the drones. And in terms of, if I just said a bit more in detail, usually we have a number of cascade controllers, a number of in-loop controller in the drones that provide us quite informative and basically stability property for the cone. If I don't know if you are a student in this area or not, but I refer you to one of our very recent papers, which is using a robust H-infinity controller for basically keeping the stability of the drones in presence of uncertainty. This is a very important also research area in control community that is applied in in this application, in this specific application.
We have another participant that wants to ask a question. Dear his or her engineer, please.
Hello, doctor. Hello, all participants. I am Hussein Mazeh. You are.
How are you doing, Hussein? How are you doing, Hussein? Good to see that you are here. Very good.
It was a very interesting presentation for you and from you and your teams. Very interesting subjects and professional work. I'm pleasure to to attend this webinar. Okay,
pleasure to have you here. Thank you, Hussein.
Okay, thanks for. I'm Hussein Mazeh. I have a master degree in robotics, and I'm interested in robotics, aerial robotics, swarms, and implementing ROS and other platforms. Okay, I have two questions. First question is implementing Voronoi partition algorithm. Is it sufficient to avoid collisions between agents? This is the first question. The second question, you said an important idea that to gain you must pain. To gain you must pain.
No gain, no pain. No pain, no gain. That's it. No pain, no gain.
No pain, no gain, yes. The subsequence or the disadvantages of distributed control is power consumption. We need more processing cost and more power consumption. Is there a plan for designing? And as we know, the path planning, okay, algorithms. We have some path planning algorithms that saves power. Okay, that choose the best path for saving power. Is there any plan for designing or implementing these algorithms, or we can say that Voronoi is the best one used?
Very good question, and also technical. Good to have some technical people who has been working on the area here. Just introduce Mazeh Hussein. Hussein is from Lebanon, and we have the pleasure to have him and his professor in past Ikram in Sharif University of Technology. That's the way we have been in touch. Yes, is Voronoi enough to avoid collision? It depends on how much uncertainty that we have in terms of the censoring. It was another question that the distance measurement, I guess Ali asked about that, and how well we are dedicated to that problem. But what we can say, Voronoi is maybe the simplest way, but not in terms of inaccurate or ineffective, no. Simplest way in terms of implementable and applicable approach to do that. And the future work, as someone informed in the last part, it is important to see what we can do in terms of the failure and in terms of what happened if this is not working in general usage. So we can use some sort of other path planning or let's say partitioning approaches as well. But in my past previous 15 years of working with drones, I find it quite reliable and effective. So we don't go to another step forward if it is not required. In terms of the second question regarding the distributed version, we are very interested to have some distributed control and to rely not on a central control system. to work toward decentralized, fully decentralized, or some distributed, as you mentioned. There are a bit different between distributed version and also decentralized version. And this is not only a matter of power consumption, and the idea is more related on the resiliency of the robot, and also the CPUs, or the computational cost and effort that we can have on on every drone. So this is the state of the art in the approaches here, and we have moved toward such approach. Of course, again, this is not the only solution, but we suggest and we recommend working in this area. And if in our future research also, we are thinking of exploring on this area.
Thank you. Thank you, Alat.
Thank you, Hussein. And I think we have some other question as well. We have a few minutes. If everybody wants to leave, I just want to say a few minutes. Maybe we can extend for 5 minutes to have other people questions and contributions into the webinar. And then we have, if it is possible, to have some pictures. I saw Gulnaz Habibi, one of my alumni, in the list. I appreciate if she can have some basically comments or question as well. Mohammed, any other question, please?
Yeah, we have 2 questions in the chat panel. And also, I would like to ask all participants to be ready and start a video to have a group photo in the end of this webinar. We have 2 questions from Mr. Abdullahi and also Mr. Rusta. Can I read it for you?
Yes,
okay.
I can read it. Here is in the chat panel.
Also.
Hi, Dr. Tagirat, could you please explain how do you solve the battery life problem? As we talked about that problem, and how many agents needed for cleaning 1 kilometer squared of oil spill, and any solution for quadcopter failure. This has been maybe, I don't know if you were thinking about this question or not, because I don't, yeah, Abdullah. Basically, this is very important. Battery life is important. Flying time is the issue here. So as I mentioned, we should have more number of drones than what is required. In the simulation, as you see, for about 200 meter square, only 10 could be sufficient. And usually, if it goes to, let's say, 1 square kilometer or so, this will be increased maybe to 20 or 40. That can be basically easily done on the initialization path on Voronoi that we mentioned, on how this could be used. And the limitation there is the sensors and the actuator that each drone has in terms of monitoring the sensor and the view that each drone can get, and in terms of spraying, and it is in terms of the limitation in terms of the actuator average area that it can be worked on. In terms of failure, this is most important part. Basically, it should be resilient. So in terms of using just simple quad rotors, as I mentioned, we use usually 8 propellers, or like X8. This was designed, and also some research with my dear friend and colleague, Dr. Ali Khaki Sadiq, has been made on the multivariable control, and also the failure, fault detection, and isolation if some of the propellant will be failed. But in any case, it is quite possible that one or more drones are not working properly, or giving failure. So it is possible to rearrange to basically have the other drones to overcome the problem. This is the topic of research that we are thinking of, the future prospect of the research, as we mentioned in the final slide. There is another question here, I see. I have two questions. Is there a possibility to use a photovoltaic cell on surface of drones to recharge the battery? I mean, can we solve this problem by this solution? Second question is when for example, one drone failed and it happened, the process of the project will, the other drones, yeah. The second one, we said, we answered previously, the photovoltaic recharging is a possibility, but considering the limited time that the drone is flying over the sea, this is not sufficient, and we should have more other state-of-the-art approach to use that. But in terms of the central home position and the recharging battery that we have on a ship or on the base, then we can use, of course, photovoltaic version. There are also some design from our group that use some photovoltaic panels on the drone as well. But as I mentioned, this is an optimization problem. You add more weight, you reduce the time, the flying time that you can provide for the drone, and that might be not a very good solution. And I guess this is a very, very important aspect of the designing a drone. Not just buying a drone, designing a drone, custom-made drone that goes for longer flight. So as I mentioned, another approach is if you are hovering, it is a flight. We can use some wings for long-term maneuvers when we have some cruise control. A combination of wings and rotors could help us in terms of the energy as well. So there is another question. Minimum number of the required UAV depends on 3 parameters, including the spill. Well, this is someone answer to the question. Thank you very much for everyone. I don't know if there is any other question.
No, I think Dr. Habibi wants to talk now. Can you hear me now, Dr. Habibi?
Yes. Hi. Hi, Professor Tagirat. I'm very happy that.
I don't know, Dr. Habibi. I know Golnaz. Are you Golnaz?
Yeah,
very well. Thank you for joining us. How are you doing?
I'm good. Thanks for inviting us. Actually, I got your email, and I'm really happy that joined this webinar. It's quite impressive. Actually, I didn't have very much. Information about the lab, ARAS, and I got a lot of, new updates from the lab. That's quite impressive. That's very great. And both your seminars and also Dr. Abdullahi and Samana Kabiri, your student and PhD student, I think that's great. So thanks for having me. I have actually 2 main questions. The first one is you talk about multi-agent system in general and all the applications that you mentioned. My question is about the scalability. How many agents that you can handle now, and also what's your view and vision about that? And I think it's one of the important questions in scalability for the multi-agent systems. And the second one, the communication, I think is more related again to the scalability, I think is also very challenging. And what's your direction to solve that communication? I think is very important in distributed systems and multi-agent systems. Thanks.
I'm sorry, I just missed the last part of the question. Maybe my internet was. Do you have my voice, Mohammed?
Yeah.
Sorry, my telephone rings and then when something happened. So very good question, Golnaz. I'm not sure if you are working on this area, but it seems that you are working on the communication level of a multi-sensor or multi-agent robot. In terms of the scale, it is a system design approach. It is a different approach that we are using, and I'm very well basically I'm very enough sorry. In the Department of Control, basically, we have divided into two fields. We have a system engineering department or group in our department, and Samane is also one of the PhD student. That's why in terms of scalability, as you as Dr. Abdullahi shows, in Beijing, China, the number of drones that can be used in just one scene this is quite amazing on how this is working. I'm sorry that this is calling so many times. I just but this is a very, very important issue. And when the system goes to large scale system, we have not only or 20, it goes to, let's say, 10, 1,000 and more. Then the scale of the problem goes, the challenges are quite different. And of course, there the resilience is important, but mostly the formation, the consensus, the issues that in a multi-agent system becomes more advanced and in terms of research. And as you mentioned, it goes the same in terms of the communication and the failure in the communication and the interferences that we have in the communications. But there are some solutions, some simple solutions that are really working. And as you see there in the Beijing, China demonstration, it is quite promising. The technology that we have is quite promising. But we should think of a large-scale system and optimal design, not just for one single drone, but in terms of a large-scale drone. And we have a group of large system and complex system dynamics and analysis in our department, and we have some sort of influential collaboration with them.
Great. Thanks for your answer. That's great. And again, thanks for having me. That's very great and very impressive seminar.
Thank you. Thank you for joining us. Yeah. And sorry to just name you because I just saw your name, which is, I guess you are our alumni for more than 10 years ago. I'm not sure how many years.
Yeah, it's much more, like 15 years ago. And I'm honored that you mentioned me.
Can you mention where are you now and what are you doing?
I'm working as a research scientist at MIT, and so this is my current. But this year I am applying for academic positions to have a more.
Perfect. Please keep in touch. And I just from this very good talk and discussion, I cordially invite all of the ARAS alumni that are present here. We have in our past 5 webinars, we were the presenters and we will present the finding of the group. Of course, we can extend it to more webinars, but I decided to have at least 1 or 2 other speakers rather than Hamid Tajirat, which is somehow boring after a few presentations. And I invite you, Golnazo, and also other very valuable alumni that unfortunately I cannot see all the names and recognize them and recall the names, but everybody, I propose to have the 6th webinar, maybe in collaboration of one of our alumni, and if it is possible, us in a special state-of-the-art approach. Of course, thank you for joining us. And I guess time is over. I would like to ask everybody to open the camera, if we can have some pictures and maybe some final, yes, very good.
Yes, regarding to your offering, that's a great offer that I will be happy to do it in the next future.
We call it for you. What about in 2 months, Golnaz? Can you perform? Just because the webinars are in a monthly basis, so not the next one, but maybe the future one. I will be in contact with you. And
sure. Yeah, and also we can talk about because I was working in different aspects of robotics, we can decide which area that you're interested in.
Yeah, maybe something that we can share together, something that.
Sure. Yeah, that
we can share together. That would be more interesting to see what is going on in ARAS and what is going on in overseas and some.
Sure, definitely. Thank you.
Professor Taghirat, can you hear me now? I think we lost the Professor Taghirat. And please, everyone, if you can, please start the video. And we have a group photo in the next couple of minutes, please. I would like to ask it in Persian. دوستان عزیز اگر صدای من رو میشنوید لطفا خودتون رو آماده بکنید و ویدیوهاتون رو روشن بکنید که ما عکس پایانی رو از تمام صفحات داشته باشیم. شاید 1 یا 2 دقیقه طول بکشه این کار، ولی ازتون خواهش میکنم اگه میتونید تصویرهای شما رو داشته باشیم که عکس پایانی رو هم از شما داشته باشیم. آقای دکتر تغییرات صدای منو دارید؟ Okay, thank you all. Please, if you can, start the video and we have a final group photo. Thank you so much. Okay. Thank you so much for having you all in this great webinar. Dr. Abdullahi, do you have any comments as a final comment, please? And dear Samane?
No, thank you. Thank you for everybody's participation and good question that they've mentioned. I hope they have enjoyed the webinar and presentation. Thank you.
Thank you. Thank you too. And dear Samane?
Thank you, everyone. Nothing more. And it's a good opportunity. I see you later in the next webinar.
Okay, thank you so much. Thank you all. We have another webinar in the next month. Please stay tuned with us and follow our news through our Telegram channel at ARAS KNTU and also our website aras.kntu.ac.ir and Professor Hamid Reza Taghirat LinkedIn page. We will share all the information soon there. Thank you so much. Thank you for joining us here in this great webinar. Thank you all, and thank you for your all consideration and for being with us in this webinar. Dear Hossein, if you have any comment, please raise your hand.
Okay, no, thank you for this opportunity.
Okay.
Good job. Thank you.
Thank you. Professor Taghirat has also come back. Can you hear me, Professor Taghirat?
Yes, thank you. I guess there is some instability in terms of the communication. As so many communication problems, the people say about the drones, we have the same with our internet. I would like to thank everybody and not extending so much more time. Very well having everybody with us. And just in 4 weeks, I will promise to have another different topic and very interesting topic, hopefully, to share with you. Be with us. Thank you very much.
Thank you so much. We can finish the session.
Bye.